following webcast is part of the Building Embedded Control Systems webcast series presented by National Instruments and Strategic Alliance Partners. Hi, I'm David LaVine with Viewpoint Systems. Today we're going to talk about the realities associated with bringing signals into and providing outputs from your control system. So what are we trying to learn about? At a high level, we're learning about the importance of interfaces. This includes interfacing to the environment, to another component, or to another system. Interfacing is important in analog and digital, as well as hardware and software realms, making the deep and detailed electrical and software engineering roles very relevant. Systems engineering is broad and brings all of these domains together, and COSI defines two roles especially relevant for interfacing: the glue role and the requirements role. So why is Viewpoint presenting on this topic? In short, we have the glue. With capabilities in systems, software, and electrical engineering, we help our customers work through requirements definition, implementation, and integration of electronics and custom software. We are system integrators. We utilize both COTS and custom components to develop a complete solution. So why does interfacing matter? I'll answer first from a technical perspective and then from a business perspective. From the technical side, if you want one component to interact with another component, there's a way this will work and a way that it won't. For example, let's say we're using an accelerometer to measure vibration. Assume that we're looking for a sine wave. If we connect an A to D directly to the sensor without interfacing considerations, our data might look something like the plot on the left, garbage. It may be challenging for the control algorithm to do anything with this information. If, on the other hand, we build up the interface with appropriate considerations, we might get something more like the plot on the right, much more usable. From the business side, it matters because the decisions made regarding interfacing will impact the cost of your product, its quality and performance, customer satisfaction, and lifecycle support. COTS versus custom component decisions are important. Considerations include the balance between lifecycle control and obsolescence management, unit cost and NRE, and a fully optimized design and time to market. Customer satisfaction is not only driven by key performance criteria, but also maintainability, return rates, and usability factors such as response rate and boot time. Maintaining a competitive advantage in the long run has a lot to do with the quality and performance of a product, which is driven in part by how well the components work together. Now that we've discussed the why of interfacing, let's discuss the what. What should we consider when trying to interface to a control algorithm? Let's start with a framework so that we can break this down into some manageable stages. Walking through the stages. We start by sensing some physical property, for example temperature. Then we condition the transduced electrical signal, maybe amplifying a small signal, maybe filtering out some noise. From there, we need to create a digital representation of the signal of interest, so we bring it into the digital world through analog to digital conversion. Next, we may need to perform some last-minute operations on the data, for example linearization, before it's ready for the control algorithm. After the control algorithm produces a result, the information needs to be provided in a particular fashion to another component or system. There's a ton of information to cover on this topic, so there are several items that will not be addressed given our time limitations. We will hit on a few key topics. We're not going to focus on sensors today, but it is important to mention the possibilities, as it will set the tone for the stages to follow. Some potential physical properties that can be sensed include temperature, sound, vibration, humidity, voltage, force, current, RF emissions, orientation, location, pressure, and optics. Typical considerations when selecting a sensor include accuracy and resolution, dynamic range, minimum detectable signal, response rate, and bandwidth. Signal conditioning. The most important aspects of preserving an analog signal revolve around grounding, isolation, and signal-to-noise ratio. SNR can be managed through various amplification and filtering techniques. Consider linearity, bandwidth, and cascaded noise figure requirements through amplification and filtering stages. From an isolation standpoint, Signal coupling and EMI can wreak havoc. Consider component and trace locations, wire locations and configuration, and EMI shielding. Consider optical isolation and transformers for more stringent signal isolation requirements. From a grounding standpoint, keep analog and digital circuits isolated from each other and minimize ground loops. Impedance matching is critical to avoid undesired transmission line effects. Sampling. Basically, we're talking about A to D converters. This allows us to bridge the gap between the analog world and the digital world, where we can perform the necessary computations to produce answers. There are several types of converters available. Consider multi-channel, scanning versus simultaneous, and direct versus sigma-delta converters, depending on your requirements. Clocking considerations. Of course, Nyquist must be satisfied. On top of that, consider some headroom for digital filtering and other processing benefits. Clock jitter. All oscillators will produce some amount of sampling irregularities. This will add noise to the system. Many algorithms assume that samples are taken at regular intervals. Digital output. Consider headroom on top of dynamic range requirements to account for nonlinearities, quantization, and transients. ENOB, the effective number of bits available out of the converter, may be significantly lower than the ideal. Pre-processing. We now have digital information. In many cases, there is more work to be done in order to prepare the data for the control algorithm. Given the processor options available today, routing of data to and allocation of processing elements, FPGAs, DSPs, RTCs, and PCs, takes some thought. Appropriate selection requires consideration of the type of operations being performed, the sequential versus parallel nature of the algorithm, response time, determinism, and throughput. Data alignment. If there are multiple input sources, data buffering and clock domain crossing may be required. Digital filtering. Analog filters are great for removing bulk noise. Oftentimes, an additional stage of digital filtering can provide sharper skirts to improve SNR further. Data transformation algorithms such as linearization and magnitude generation may be required. Data integrity. Be on the lookout for wrapping and overflow conditions. At this point, we have provided the control algorithm with the data it needs to make an intelligent decision. This data is provided at the right time, with the right range of values, and in a digital format that the algorithm understands. Once the algorithm produces an output, that information needs to go somewhere and interface to something. It turns out that post-processing, signal conversion, and signal conditioning on the output side have similar associated considerations as on the input side, so for the sake of time, we'll blast through these sections with a single interesting note. Some systems have very symmetric input and output stages, while others do not. Where do your systems fall on the spectrum? Actuators and control. At the final stage, typical goals are to physically control something or to communicate information to an external system or person. We accomplish this with actuators and communication interfaces. This could include interfacing to hydraulic, electric, or servo actuators. Communication interfaces could include Modbus, USB, Ethernet, RS-485, EtherCAT, CAN, Wi-Fi, or cellular. We've now closed the loop from sensing our environment to controlling it. Next up are a couple project examples where Viewpoint worked with our customers to help them develop their embedded measurement and control systems. Solution number one is for improving a machine used to manufacture gears. The input utilizes an NI digital input module to monitor digital rotational encoders. Pre-processing involves smoothing discrete angle-based measurements followed by order analysis. The output utilizes an NI analog output module to apply dynamic torque adjustments. Solution number two is for a smart grid analysis application. In this case, a hybrid COTS plus custom solution allowed us to meet reduced cost targets while satisfying technical requirements. Viewpoint designed a single board Rio daughter board with 8 analog input channels with simultaneous sampling at 50 kHz and 16-bit resolution and a GPS receiver for timing synchronization requirements. This information is passed to another set of subsystems where some black box processing and control take place. The world of interfacing is ever evolving, with a continual stream of technologies and techniques for conditioning coming out all the time. This drives evolution in the COTS versus custom decision-making process. Follow this link or the webcast page link to learn more about how Viewpoint can work with you to solve your I/O challenges. You'll find info related to this webcast, including case studies. Thank you for attending this portion of the Building Embedded Control Systems webcast series. You can view additional webcasts at www.ni.com/buildcontrolsystems.